So in this video, we're going to be looking at enthalpy changes, right? Now, enthalpy changes itself is just a posh word for saying energy change, right? And we look at enthalpy changes in A-level because it's a proper scientific term. Now, let's say if I were to look at enthalpy change, we define that as being the heat energy transferred in a reaction at constant pressure. Now, when we look at the units of enthalpy change, we say that we're dealing with the energy transferred in kilojoules when we're looking at 1 mole of a substance itself to make our values actually comparable. Now, looking at standard states are going to be the states, the physical states our compound is going to be in under standard conditions. What's meant by standard conditions? Well, we say that a compound, right, to have standard conditions, it must be under a pressure of 100 kilopascals, a temperature of 298 Kelvin or 25 degrees Celsius, and then if we're dealing with concentrations of solutions, it's going to be 1 mole per decimeter cubed as well. Now, if I were to look at, right, shortening all of that information, I could just say, instead of standard conditions, listing them all, I can actually just show this little symbol over here. But the examiner actually prefers you to use this and this over here when dealing with enthalpy change. Now, there's 4 definitions that we need to actually be aware of. The first one, the most basic one, is going to be about the most basic enthalpy change, which is the standard enthalpy change of reaction, which you can see we've got a symbol delta HR and then our little underground symbol over here. And this enthalpy change is when we have a reaction that occurs in the molar quantities shown in the chemical equation with all of our reactants and products in their standard states under standard conditions. And so, as an example, I've got here the reaction between carbon monoxide and nitrogen dioxide to form carbon dioxide and nitrogen monoxide as well. Now, normally when we deal with the standard enthalpy change of reaction, we normally use that when we can't define our enthalpy change as being either the standard enthalpy change of combustion, neutralization or formation itself as well. Now, let's say if we were to look at our next 3, right, starting off with our standard enthalpy change of neutralization, which you can see here in subscript I've got new. This is the enthalpy change when solutions of acids and alkali react together, and the key part here is to form 1 mole of water under standard conditions. And let's say if I looked at an example with reacting sodium hydroxide with something like, let's say, H2SO4 sulfuric acid as a product, what I'm going to actually form is sodium, and then it's going to be 2 sulfate itself, and then I'm going to form water as well. If I were to balance this, I end up with 2 lots of water and 2 lots of sodium hydroxide. Now, this in fact is going to be the standard enthalpy change of reaction if I were to look at the enthalpy change, so that would not actually be the standard enthalpy change of neutralization. To make an equation for the standard enthalpy change of neutralization, I need to divide this by 2 over here. I need to divide the entire equation therefore by 2 to get 1 mole of water, and so what I end up with is sodium hydroxide reacting with 0.5 lots of H2SO4, and then I end up forming, right, half a lot of Na2SO4, and then I end up forming water as well, right? So there I have my standard enthalpy change of neutralization equation for the reaction between sodium hydroxide and sulfuric acid itself. Now, what about the next equation where we're dealing with the standard enthalpy change of combustion? Well, in this case, right, we're looking at the enthalpy change when 1 mole of a compound is completely burned in oxygen under standard conditions itself. And let's go with propane as an example. So that's going to be C3H8, and that's going to react with oxygen, and what we're going to end up forming is our products, which is going to be the complete combustion products of carbon dioxide and then water as well. Well, if I were to balance this, I'm going to have 3 lots of carbon dioxide, I'm going to have 4 lots of water, and then I'm also going to have, in terms of the number of oxygen atoms, I'm going to have 3 times 2, that's going to be 6, 6 add 4, that's going to be 10. I end up with 5 lots of oxygen atoms itself as well. Now, if I had, let's say, double this equation, so let's say if I had 2 lots of propane being burnt, that would not actually be classed as the enthalpy change of combustion. It would be the enthalpy change of reaction itself as well. Now, what about the last definition, the standard enthalpy change of formation this time, which you can see over here, we've got an F in subscript compared to a C over here in subscript. This is actually the enthalpy change when 1 mole of a compound is now formed from its elements in their standard states under standard conditions. And so let's say if I were to look at forming 1 mole of propane, right, this time we're actually going to have that in our product. I'm going to include some state symbols as well, where I actually end up with, in this case, a gas being formed from its elements in its standard states. We've got hydrogen that exists as H2, that's going to be a gas in its standard state, and then we're going to have 4 lots of that, and then we're also going to have 3 lots of carbon, that's a solid in its standard state as well, right? If I were to include state symbols over here, right, I've got a liquid, I've got a gas, and then I've got a gas again, And then I've also got another gas over here as well. But normally we need our state symbols when dealing with the standard enthalpy change of formation, just like how we have over here. Now, when we look at enthalpy changes, right, we normally deal with something called a system, which is normally a reaction in chemistry, and everything outside the system is going to be known as the surroundings. And when we look at, right, let's say our enthalpy changes, we can either say that they're going to be endothermic, right, where we end up with energy going from our surroundings to our system, and we end up with a positive value for our enthalpy change, or we can end up with a negative enthalpy change itself, where we end up with our energy going from our system to our surroundings itself as well. Now, if I were to look at these two terms, you can see that an exothermic reaction is going to be negative in terms of its enthalpy change. An endothermic reaction is going to be positive, and really it depends on how much energy is being absorbed and released by the reaction itself, and which one weighs out more. Now, when we look at these processes, right, really we talk about it in terms of bond forming and bond breaking. Bond forming from GCSE, we know that's going to release energy. Bond breaking is going to absorb energy. And if we were to look at this, right, in a bit more detail, at the enthalpy change of neutralization, because we're forming a bond between the OH minus ions and then the H plus ions itself, right, what that actually does is to form that molecule of water, it actually releases energy. Bond forming releases energy. So we know in that case, right, this is going to be a negative enthalpy change, and it's also going to be an exothermic process as well. So if I were to, let's say, look at combustion reaction, right, we could normally say that our enthalpy change is going to be negative, right, and we also know that our enthalpy change, right, we can call that exothermic as well, because in this case, right, the bond formation, the energy released is going to be greater, much greater compared to the energy absorbed for breaking your bonds itself. Yeah, so looking at the next one then, what about the standard enthalpy change of formation? Now, normally this one's going to be exothermic in terms of a process itself as well, but right, in some cases it can actually be a positive enthalpy change, and so it could actually be endothermic, and that is only when the bond forming step is going to be outweighed by the bond breaking step. But again, right, it's pretty much hit and miss. In most cases it's going to be exothermic itself. So yeah, moving on, I've got a short task for you to do. I want you to assign the following reactions as being either the standard enthalpy change of combustion, formation, reaction, or neutralization. It's always best to check neutralization, formation, and combustion first. If it doesn't fit any of those, then it's going to be the standard enthalpy change of reaction itself. So yeah, starting off with the first one, we're burning 1 mole of a fuel to form carbon dioxide and water. We can see we've got complete combustion over here as well. So that's going to be delta HC. And it doesn't really matter about the C coming before the H or after the H. It's both the same thing, both accepted in the exam. What about the next one? I've got H plus reacting with OH minus, that makes water. We're forming 1 lot of water, so we know straight away that's going to be the enthalpy change of neutralization. Looking at the next one, right, I've got carbon sulfide, right, 1 mole of carbon sulfide reacting with oxygen to form carbon dioxide and sulfur dioxide. We've still got combustion reaction over here, and so we know, because we're burning 1 mole of fuel itself completely, we end up with delta H, right, and then it's going to be C, standard state symbol as well, and there's that one done, that's combustion. The next one, right, a bit more challenging over here because D and E look very similar, but if I were to look at D, we're forming 1 mole of a compound from its reactants in their standard states, so it can be considered to be the standard enthalpy change of formation in this case. But again, because we're burning sodium itself, right, you can actually see this as being the complete combustion in this case, because that's technically what we're doing, but of course we prefer to go with formation instead. If I were to look at the next one, I've got sodium reacting with oxygen and I'm forming sodium oxide, so it's not going to be combustion because I'm not actually burning 1 mole of fuel or 1 mole of a substance. It's not going to be formation because I'm not forming 1 mole of a substance, I'm forming 2. The only one that fits in is going to be the standard enthalpy change of reaction, which is going to look like this. So moving on, right, feel free to have a go at the following examples. This time I want you to write the equation for the formation equations and the combustion equations as well. So yeah, looking at the first one, right, we're going to be forming 1 mole of butane from its elements in its standard states. So in this case, we're going to have the following formula of C4, and then it's going to be H10. And remember, that's going to be a gas. If I were to look at my reactants, let's say, right, in this case, I'm going to have 4 lots of carbon atoms, 4 lots of carbon, that's going to be a solid, and that's going to react with 5 lots of hydrogen, that's going to be a gas as well. If I were to look at that, right, that's going to be correct. I'm forming 1 mole of a compound from its elements in its standard states under standard conditions. If I were to look at propan 1-ol, right, I'm going to have here C3, and then it's going to be H7OH, right? I can leave it as that, or I can put the molecular formula. It's going to be a liquid because most of our alcohols are going to be liquids as as well. And if I were to look at what that's formed from, I've got 3 lots of carbon, that's going to be solid this time, reacting with, right, it's going to be 4 lots of hydrogen, that's going to be a gas this time, and that's going to react with half a lot of oxygen, and that's going to be a gas as well. And so there I've got the equation for the standard enthalpy change of formation for propan 1O. If I look at the next one, I've got magnesium oxide, which is going to look like this. Ionic compound, that's going to be a solid at room temperature and pressure. And we know the following, that we've got, right, magnesium oxide being formed from magnesium, the metal, which is solid, and then oxygen, half a lot of oxygen, which is going to be a gas as well. Remember, you need to keep the magnesium oxide, the product itself, as 1 mole. So you need to use fractions in this case, or decimals, to balance your equations. And don't forget to include your state symbols, because you actually lose a mark for that itself as well. I'm just double checking here, and I can see I've included all of my state symbols over here. So yeah, looking at the next one then, we're asked to write equations to show the enthalpy change of combustion for butane, propan 1O and magnesium. And so in that case, right, butane, nice and easy, I'm going to end up with C4H10. I'm not going to bother with state symbols in this case, but in some cases they can actually ask for them. I'm going to react that with oxygen, and what I'm going to end up actually forming is carbon dioxide, right? I'm going to form 4 lots of carbon dioxide, and then I'm going to form 5 lots of water as well. If I were to look at my actual balancing of the oxygen atoms, I'm going to have 5 added to 8, that's going to be 13. 13 divided by 2, that gives me 6.5 lots of oxygen molecules to make up for 13 atoms. If I look at propan 1O in this case, right, I'm going to have C3H7OH. Just remember, you've got an internal source of oxygen over here that's going to react with oxygen, and we end up forming, right, in this case it's going to be 3 lots of carbon dioxide, and then we're going to have, right, 4 lots of water itself as well. Now if that's the case, right, I can see in terms of oxygen, I've got 10 lots of oxygen on the right hand side, 4 added to 6, that's 10. Subtract 1, because I've got this internal source of oxygen over here, that's going to leave me with 9. Divide by 2, that's going to be 4.5 lots of oxygen itself. What about magnesium? Well, we know magnesium, 1 lot of magnesium is going to burn with oxygen, and what we're actually going to end up forming is magnesium oxide itself. Again, we've burned 1 lot of magnesium, right, so we must use 0.5 lots of oxygen to make that balance as well. And there is my 3 other examples of the standard enthalpy change of combustion, in this case done, along with the 3 above that for the enthalpy change of formation. So yeah, moving on in that case, right, if we look at enthalpy changes in a bit more detail from GCSE, we know that we need to deal with something called the activation energy as well. And the activation energy is the minimum amount of energy needed for a reaction to start. And normally, right, we represent this using this following symbol over here, where we've got capital A, and then we've got in subscript, we've got a small a as well. That is a symbol for activation energy, and you'll come across that quite a lot as well. And normally activation energy is going to be an endothermic process. It's positive because you've got to put energy into the system as well. So we can say that that is actually going to have a positive value if we were to look at the actual energy itself. Now, when we look at the units for activation energy, we can normally deal with that in terms of joules per mole, or we can deal with it in terms of kilojoules per mole as well. Just remember, if you're going from kilojoules to joules, you're going to times by 1,000, and if you're going from joules to kilojoules, you're going to divide by 1,000 as well. So coming back to our exothermic and endothermic reactions, right, an exothermic reaction is defined as a reaction that releases energy with a negative enthalpy change itself. And you can see over here, right, I've got the standard enthalpy change of combustion, which we said is normally going to be negative itself, and you can see here we have 890 kilojoules released in terms of energy per 1 mole of a substance that we're actually reacting in this case. And so, right, we can actually say that this is going to be exothermic because heat is going to be exiting the reaction itself. Energy is going to be exiting the reaction. That's how I remember it. Now, what about if I were to look at endothermic reactions? Well, in endothermic reactions, we're actually absorbing energy, right? So the reaction, the system itself is going to absorb energy. So an endothermic reaction is actually defined as being a reaction that absorbs energy with a positive enthalpy change. And you can see that over here, right, we've got a positive enthalpy change, so we know it's going to be endothermic, whereas over here it's going to be a negative enthalpy change, so it's going to be exothermic itself as well. And you can see that because we're actually burning a substance over here, whereas over here we're putting heat energy into the system. And so what we're doing is we're breaking calcium carbonate down to form calcium oxide and carbon dioxide itself. In this case, right, you know this reaction from GCSE has been the thermal decomposition of calcium carbonate. You're going to heat it up and it's going to break apart into calcium oxide and carbon dioxide itself. Now let's look at the following reaction over here, which we know clearly this is going to be an exothermic reaction because we've got a combustion reaction. At the same time, we've been given a negative enthalpy change. Now, if we have a negative enthalpy change, right, we can draw an exothermic reaction profile, enthalpy profile diagram, enthalpy change diagram for our actual reaction itself. And you can see over here, I've got on my x-axis the progress of a reaction. On my y-axis, I've got the enthalpy itself, right? And we can see that we've got a line for our reactants, which I'm going to draw very quickly. I've got methane over here, so I'm going to draw it exactly as it is, balanced as well. So I've got CH4 gas, and then I've got 2 lots of oxygen. That's going to be a gas as well. And then for my products, I'm going to have carbon dioxide, which is going to be a gas. And then I'm going to have 2 lots of water, which is going to be a liquid in there as well. Now, in this case, right, you can see the following over here. I've got reactants and products, and we can see that we've actually got a difference in terms of enthalpy. Enthalpy is going to decrease going from reactants to products, but, right, it has to be going somewhere because energy can't be created or destroyed. It can only be transferred. We know that energy is going from our system, right, which is represented by this little diagram over here, to our surroundings itself, which is going to be any decrease. So let's say if I decrease from here to here, any remaining energy within this distance is going to be released to the surroundings. That's how we know it's going to be exothermic as well. Now, let's say if I were to start off by drawing my curve to begin with, so I should end up with something that looks like this, right? What I've actually got over here, right, is my progress of the actual reaction and how enthalpy changes as the reaction actually proceeds. And you can see over here that enthalpy is going to slowly increase up until a point where it peaks, and then it rapidly starts to decrease. Well, we actually call the distance between, let's say, this line over here of our reactants, which I'm going to draw a extrapolated line for, right? We can see that we end up with a certain amount of energy needed, right, to reach this peak, and that energy we actually call the activation energy itself as well, and we represent that using a symbol of EA, right? That's our activation energy. Remember, the A is going to be subscript. That's going to be the minimum amount of energy needed for our reaction to start, because our reaction is going to start at this point over here once we've reached a certain energy, once we've reached a certain enthalpy in this case. So yeah, right, that's one thing that we could also do. If I were to draw my next line on there, right, my next label, I've got over here another line, and this line is going to help me show the difference between the enthalpy change itself. And so let's say if I were to look at the following, I'm going to have enthalpy actually decreasing. So in this case, I'm going to draw my arrow going downwards. I'm going to show that I've got enthalpy change over here as well, right? You can see that enthalpy is decreasing, and we're going from this value over here to this value over here, right? At this moment in time, I haven't actually got any calculations or any values for enthalpy change, but I'm just given a diagram on what you need to be able to draw in the exam itself, right? So far, I've got my reactants, I've got my products, I've got my products that are going to be lower than my reactants because it's an exothermic reaction. I've got an arrow pointing upwards, and it's very important that it points upwards for the activation energy, because remember, it's an endothermic process. And I've got an arrow pointing downwards for the enthalpy change, because remember, we've already discussed that this is going to be for an exothermic reaction itself. And so far, this should actually give you 3 marks itself. Just one thing to be aware of is that your arrows, can you see over here, it's not actually touching the line. You need to make sure it touches the line on the dot. Same thing with this one as well. You need to make sure that you're touching the top and the bottom line. It's always helpful to use a ruler as well. So in that case, right, we've actually drawn an enthalpy profile diagram for an exothermic reaction. What about an endothermic reaction itself, right? How do I know this is an endothermic reaction to begin with? Well, we've got an enthalpy change that's going to be positive in this case. And we can see we've got here our same example we discussed before, the thermal decomposition of calcium carbonate itself. Now, this time you can see that my reactants are going to be lower in terms of enthalpy compared to our products. That means that enthalpy is going to increase, but where's the energy going to come from? Well, it's going to come from the surroundings, and it's going to be absorbed into our system, our reaction itself, right? So again, I'm going to start off with the same curve. I'm going to draw something that looks like this. So again, I'm going to draw my first line that's going to be over here, and that's going to be level with this line over here. And what we need to do is make that dotted as well, so we don't get confused or confuse the examiner, which is even worse. And then we're going to have this time, right, our enthalpy change. We'll draw that first of all, and we can see that we've got an arrow going from the bottom over here to the actual products itself as well. And we can say that again, enthalpy change is going to be positive. It's going to be an endothermic reaction, so our arrow points upwards itself. Now, what about activation energy? Well, activation energy, again, is going to be the minimum amount of energy needed for a reaction to actually start. And let's say if I were to actually draw my arrow, it's going to be pointing upwards again, because remember it's an endothermic process. I'm going to end up with something that goes all the way up to the peak itself as well. So I'm going to need this much energy for the reaction to start. And so what I can now do is I can label that again, your arrow points upwards because it's an endothermic process. And so you can see over here, right, that we've actually got our bond breaking step, which requires energy. So once we've reached our activation energy, our bonds break. And then after that point, that's when our bonds actually form. And the overall process is going to be the enthalpy change, which is going to be positive in this case as well. So yeah, I'm going to go ahead and write in my reactants, which is just going to be the same. The only thing that changes is the reactants really. That's going to be calcium carbonate, which is a solid, and then I'm going to have calcium oxide, which is also going to be a solid, and then I'm going to form carbon dioxide, which is a gas as well. And so here I have an enthalpy change diagram for a endothermic reaction itself, and roughly you do get another 3 marks over here as well. Now, one other thing to note before we actually move on, right, if we were to look at, let's say, reversible reactions, let's say reactions that can have a forward reaction and a reverse reaction, all we do is we flip our perspective. And so this would flip over here, this would flip over here. The enthalpy change would actually be the same overall. The only thing that would be different is the activation energy. So let's say if I were to look at the activation energy for the forward reaction, it's going to be the distance from there to there. But then if I were to look at the reverse reaction, I end up with a distance from there to there itself as well. That's just one thing to be aware of, and we'll see that in the exam question that we do together now. So I want you to pause the video and have a go at the following question, and then resume once you're ready to move on. So yeah, a reversible reaction has the enthalpy profile diagram shown below over here, and we're asked which statement about this reaction is going to be correct. First of all, the activation energy of the forward reaction is going to be 120 kilojoules per mole. Well, if I were to look at this, right, the forward reaction, there's distance between here and here, which you can see the examiner's actually already drawn in for us, but without an arrow. That's going to be 150 kilojoules per mole, so that's going to be incorrect, because remember, your y-axis values are actually given over here, right? So that's going to be 150, not 120. The reverse reaction is exothermic. So again, if I change my perspective, if I start off with here, my products, which is going to be my new reactants, going to form my reactants, which is going to be my new products. In this case, right, we can see enthalpy is going to increase, right? So if we're going from products to reactants, going this way, enthalpy increases. So we know it's actually going to be endothermic. So that's going to be incorrect itself. The forward reaction is going to be exothermic because enthalpy is going to decrease itself. What about the next one then, right? If I were to look at the next one, the enthalpy change of the forward reaction is minus 30 kilojoules per mole. Well, if I look at the forward reaction itself, right, I can see that I've got 150 kilojoules per mole for my actual activation energy, which is going to be the distance, right? Again, as I mentioned, between there and there. But then if I look at the distance between reactants to products, that's going to be my enthalpy change. So that's going to be 120. And it's saying that the enthalpy change of the forward reaction is going to be minus 30 kilojoules per mole. That's going to be false. It's actually going to be 120. That means the last one is going to be correct. The activation energy of the reverse reaction is going to be 270 kilojoules per mole. That's going to be correct because we know the distance going from here to there is going to be 120 added to 150 itself. And together, that is going to make a value of 270 kilojoules per mole. So we know the correct answer is going to be D in this case as well. So moving on then, I've got another task for you to try. Feel free to pause the video and have a go. So yeah, hydrogen and chlorine react as shown below. Hydrogen reacts with chlorine to form hydrogen chloride. And we've got an enthalpy change, which is going to be minus 184.6 kilojoules per mole itself. Which statement about this reaction is going to be correct? A, less energy is released on bond making than is taken in during bond breaking. Well, we know if you've got an exothermic reaction over here with a negative enthalpy change, right, we know that in terms of bond breaking, which is an endothermic process, we're going to absorb energy, that's in our reactants, and in bond forming, in our products, that's going to release energy. And because we've got a negative enthalpy change over here, we know that more energy is released than taken in. So if I were to look at a system, right, we can end up taking in a tiny bit of energy, but releasing loads more energy, and that's why we end up with a negative difference itself as well. So in that case, right, we know that bond forming is going to be greater than bond breaking. So in this case, this is actually going to be incorrect itself as well. If I were to look at the next one, the temperature decreases during the reaction. Well, that is actually going to be false because we know that if you've got a negative enthalpy change, if energy is going to increase in the surrounding area, so if energy is being released, that's going to be released in the form of heat. Looking back to our enthalpy definition, formation, and so we know that's going to be false. If you look at the enthalpy change of formation of HCl, right, in terms of formation, we know that HCl, we need 1 mole of that. In this case, we've got 2 moles. It's saying that it's going to be negative 184.6 kilojoules per mole for the enthalpy change of formation, but we know it's going to be half that amount, because in order to have the enthalpy change of formation, we need to have half a lot of hydrogen gas. That's going to react with half a lot of chlorine, and that's going to react to form, right, 1 lot of HCl gas itself as well. So we need to bear that in mind. So our value for the enthalpy change of formation would actually be half this value of minus 184.6, and so what we'd expect to have instead is going to be minus, and then it's going to be 92.3 kilojoules per mole itself. If I were to look at the next one then, right, which is going to have to be right, the enthalpy change for the reverse equation is going to be positive 184.6 kilojoules per mole. Well, we know if the forward reaction is going to be exothermic, the reverse reaction in that case, it must be endothermic by the same enthalpy change. The only thing that's going to change is our activation energy itself, and so we know, right, in this case, that's going to be correct. The enthalpy change stays the same.